You may have seen my video looking at using Wireshark to capture the messages that are flowing on the CANBus, in particular in my case the CAN bus, on my BMW E87 aging 1 Series circa 2006 car. So just to give a bit of background in case you haven't been following my race car build series on YouTube, I'm building a car to compete in the 116 Trophy series here in the UK, and the car's stripped out. I mean, there's not a lot left inside, and one of the things, or two things you do take out, one is the parking detector system, that the little ECU that sits in the boot of the car or in the trunk, and the other is the airbag unit, and all the airbags have been removed. All of the seat occupancy detectors have been removed. The seat buckle detectors have been removed because obviously I'm running a racing seat with a full harness seatbelt setup. So all of these things have been removed, and the sum total of all that means that I get, when I start the car, I get an airbag and seatbelt warning light come up. Now, it's quite normal on these cars to race like that. I've been racing one of these cars all season, and those two indicators have been on throughout the whole season in the car I've been racing. So it's not unusual. But I'm trying to figure out a way of extinguishing those indicators so that I've basically got no errors on my dashboard at all, unless something actually goes wrong. And that's what got me into looking at CANBus and seeing if I could simulate the messages that come from the airbag unit. So the airbag unit, I've seen it called the SRS unit, which I think is Safety Restraint System. I've seen it called MRSS, which I think is Multiple Restraint Safety System, something like that. But it's the little ECU that sits under the center console just behind the handbrake. Okay, so that's the starting point. So the objective is to extinguish these lights, and I started explaining a bit about this in my previous video, but somebody kindly commented, gave me some feedback and said this is pretty heavy stuff, and you know, he was struggling to understand it, and I think he was a computer science major, and he's got a good point. I just dived in, you know. So I'm going to try and add some background. So you'll find lots of videos on YouTube. A lot of them cover the physical and electrical aspects of CANBus. And the one, a set I really like, on a channel called Mechanic Mindset. The guy on there goes into some really great detail. He starts from quite simple digital multimeter type readings into using an oscilloscope to look at the signals flowing, you know, the encoding of the messages on the CANBus. There are very few videos covering protocol analysis. The one I used was one on a channel called Pengutronics. Pengutronics has got a lot of, well, as you might have expected, a lot of Linux stuff on it, I think. But you will find a CANBus analysis video on there, and he does it in a very straightforward way with a nice controlled setup. So that's worth looking at to gain some background. So let's talk about the setup on the car. So as I said earlier, I've got a BMW 1 Series. It's old. The 116 Trophy Series is based around cars E87s from 2004 through to 2006. So the engine variant is N45, if you're familiar with that. This is a very simplified diagram, and it's drawn in a way that you don't usually see it drawn. You usually see it drawn in a sort of hierarchical way, but I wanted to draw it like this because there's a couple of things I wanted to point out. You see that we have three different CAN buses. We have one called the powertrain CANBus, and the data speed on there is 500 kilobits per second. We have one called the FCAN. I don't know what F stands for actually, I must admit, but that's also running at 500 kilobits per second. And then we've got the KCAN, which is running at 100 kilobits per second. And the thing that links the three CAN buses together is a unit called the JBE, which I've also heard referred to as a gateway. To me, the closest, because I expect there might be some computer literate people watching this, the closest thing I can think of it is like an Ethernet bridge or switch. So we've got that. Now we've then got lots of different control units attached to these various CAN buses. So there is a way, I believe, to send requests to one of these control units and get a response. But I haven't really analysed any of those message formats. Everything I've analysed so far has been an asynchronous notification. What I mean by that is that, say this unit here, the DME, just throws a message out onto the CAN bus, and that's all it does, just repeatedly keeps throwing the messages onto the CAN bus. Now the message has an identifier in it, and we're going to look at this a bit later, but it's got an identifier, and if, say, the DSC was interested in the message with that identifier, it would simply copy that into its memory and start to process that message and do whatever it wanted with that message. And all the other units do exactly the same. They simply throw messages onto the various buses. The DME, well, actually, one good one is the DSC and the instrument cluster definitely communicate with each other. And if I watch messages over here, and the way I do that is I attach a PC with this thing called Wireshark. If I watch messages over here, I can see DSC generated messages arriving over here. So they're passing through here. Now, as they pass through, you can see we've got two different data speeds. So here we've got a clock speed that achieves 500 kilobits per second, and over here we've got a different clock speed. So what that means is it's not simply what's called an electrical repeat of the messages here. The frame must be taken in, reframed, and then sent out, and that's one of the functions of the JBE. Now, because it does this reframing, it has the opportunity to actually filter. So it could decide that the message that it receives down the PT CAN should not be sent onto the KCAN. Now, one of the reasons you might do that, and you can actually see there's a big hint here with these data rate numbers. If you imagine that on this CAN we are using, say, 25% utilization of this CAN, of this bus. So perhaps we're using 125 kilobits per second. And let's say we're doing the same on the FCAN. So that's a total of 250 kilobits per second. Now, if I pass all of that data onto the KCAN, you can see it's going to overload it. So, I suspect there are lots of messages that flow on these high-speed CANs that do not arrive on the KCAN. So that's worth knowing, that not everything is going to pass through. Whether everything from here passes onto these two CAN buses, I don't know for certain. I mean, a lot of this is like reverse engineering the stuff, and I've only just really got into it, so I'm learning as I go. Now, messages between, say, the MRSS unit, the airbag unit, and the instrument cluster are travelling on the same CANBus, on the KCAN. Now, although I'm showing this logically like this, it could be that everything is what's called star wired out of the JBE. So it could be that there's a twisted pair that goes from the JBE to the instrument console, twisted pair that goes from the JBE to the MRSS, twisted pair goes from the JBE to the PDC, etc. And I haven't explored that, but logically they're all on the same bus. So the electrical signals are simply being repeated onto each pair. One question you might have is, well, where does the OBD port fit into this? So and this is, remember we're talking about an old E87 here. There is not a CAN connection into the OBD, not as such. There is a K-line connection, and it's the K-line that talks to the other, to each unit. So, for example, if you're running a scan via the OBD port, and you're, say, pulling information like codes out of one of these control units, that's flowing over the K-line. I actually checked this myself. What I did was I ran a scan against the instrument cluster, and I captured the packets using Wireshark. And although I could see instrument cluster packets, I couldn't see anything associated with the scan that I was running. So, for example, in the scan, there's a thing about version, software version numbers, and there's some sort of ID in there. And I looked for ASCII strings and binary encoded integers and all sorts to try and see if I could find the data, and it's not there. So that's flowing outside of this CAN structure. It's flowing like this. But one of the reasons I got into all of this was because I connected my AIM data logger to the OBD initially, and you don't see all the metrics. You see a subset of the different bits of information out of all of these different units, and that's because I think they're coming through the JBE. So as each of these is sending these notifications, that lots of people refer to it as a broadcast. So as they broadcast the information, not all of it is coming down this connection and into the OBD, onto the K-line and into the OBD. So you see a subset. That's one of the reasons why I decided to do away with my OBD connection for my data logger and connect the data logger directly into the CANBus. In fact, I connected it into this one here, into the PT CAN. Okay, so enough of all of that. Let's actually look at some data. So this is if you just run with the default Wireshark profile, and the profile just gives you the layout of the screens. If you just run with the default and you load up at one of these CAN traces, you'll have to refer back to my previous video to see how I captured it. But if you load up one of these, what you'll get is this pretty horrible format. In fact, you don't even. I've actually messed up my own. Let's get rid of that. It actually looks like that. That's how it looks by default. Now I'm going to create a new profile, and I'm going to call it CANBus. Okay, so now I have a new profile. It's based on the default, so it's not got any. It's not any different from what you saw before. So these are the changes I'm going to make to this profile. First thing I'm going to do is I'm going to change the time display format to time of day, because I prefer it to be time of day. So you can see I captured this trace or packet capture at 10:46, and in fact if I go into here you can see I did it on November 21st at 10:46. So it's got full details about when this was captured. The next thing I'm going to do is I don't really need this source and destination column because these refer to Ethernet columns, and I don't really need those. I know it's CAN, so I don't really need that. Actually, I might leave that in just in case I was to pick up something else. Do I need the length value of 32 bytes? Well, all CAN packets, all CAN frames are 32 bytes long. I think we'll leave that for the moment. We'll leave that. Actually, that's what I just said there is not actually true. Just to confuse things. Wireshark has stuck its own 16-byte header on the front of this. That's very unusual. Wireshark doesn't do that. But if you look here, it says this is a Linux cooked capture. It's just something that it does. So in fact, those first 16 bytes of this capture are not actually flowing on the CANBus. The CANBus message starts there. So let's now open up what we have. So here's the first thing. We've got an identifier, which is called the CAN ID, and then we've got some flags. This is just showing you that they're bit masks. So for example, I'll explain one of the bit masks. A normal CAN ID is 11 bits long, so you can see there's 11 bits of information there. You can have an extended one, which is 19 bits long. If that was set to 1, then you would have 19 bits of CAN ID. But on an E87, we only see standard length CAN ID, so we can ignore that. I've yet to work out what these other two things really mean. I've got some theories, but it's not really worth me talking about my theories. And then we've got, so that's 2 bytes. Then we've got, oh, that's naughty. Oh no, that's not 2 bytes, is it? It's 4. 1, 2, yeah, sorry, it's 4 bytes. 4 bytes, of course it is. Okay, yeah, so there's 4 bytes there. Which refers to this lot, and then we've got a frame length value which is looks as though it's 2 bytes long. No, it might only be 1 byte long. Yeah, 1 byte long, and 3 bytes of zeros which are reserved. So this is the standard CAN header, and this will be the same across any car that you look at. This is encapsulated, if you like, in the CAN protocol definition. Then comes the problem. Then you've got the payload, which is this lot here, or what you see here. What you include in your CAN packet as payload is totally up to you. It can be complete nonsense. It's the person who's writing the code that generates the CAN messages, the CAN frames. They can decide what goes in here. When I check the documentation for my, let me see if I can find this, documentation for my AIM data logger, it tells you about the 2 different types of connections. I already mentioned you can have an OBD connection, and you can see there it talks about K-line, which is the thing we mentioned earlier. Or you can have what they call an ECU connection, which is actually a powertrain CANBus connection. So you can see it says CAN high, CAN low, and these are the colours that are on my car. Apparently you can have different colours on some cars, but my car's got these colours. On the powertrain CAN, I should add, because the K-CAN colours are different. But the powertrain CAN colours, these are the correct colours. And you can see that it calls, so the OBD protocol is apparently standardized in a document ISO 9141-2. But here's the one for the CANBus, and they call it BMW PT6. And I've seen PT6 mentioned somewhere else, but I can't remember where. But anyway, I've sort of referred to it in my own notes as PT6 as being the protocol. I can't find any document that defines PT6. All you can do is reverse engineer the messages, which is a really tall order, except for a guy who runs a website called loopybunny.co.uk has done a lot of work decoding them. So you can see all the CAN IDs down here, and then you can see the contents. And in fact, if you click on one like torque, clutch and brake status, he then gives an explanation of the breakdown of the payload and the calculations that you can do. Now, you can see he's based this on a BMW X1 E84. But if you go, if we go, back to his homepage, if I can just do that, he's got this filter and it says KCAN1 E8X, implying it's all E8, 84, 81, 87 values. I don't know how true that is, but anyway, we can put in a filter. I'm finding that I am getting some differences in what I'm finding, but this is a good starting point. It certainly gets you, just gives you a kickstart into looking at how to decode these messages. Okay, so let's look at one. So if we look at where is it? I want the braking force, ABS and braking force. So I did a little test. You can see I've got brake pressure here. Now what I'm going to do is I'm going to put the data in this packet list at the top. So let's move the data up to there. And then I'm going to do a filter for 0x19E, was it? Let's go back and have a look. 19E, ABS force and braking, yeah. Okay, now there are a whole bunch of things that are changing here. There are some funny counters that cycle and other things, but what I want you to do is concentrate on this block of zeros. Let's see if we can make that a bit bigger. This block of zeros here. So what I did during this test is I sat in the car, switched all the ignition on. I didn't start the engine, but I switched all the ignition on, and then after a period of time I pressed the brake. So whoops, okay, so we're looking at these zeros. So what you can see here is that I must have pressed the brake at 10:47:18.622, pretty precise. And the brake force is gradually increasing. Which way round do you read this? Well, it looks as though, yeah, that's surprising. Yeah, so it could only be, maybe it's only got a granularity of 255 data points, single byte, but you can see the numbers increasing there, and then we should find that it decreases after I take my foot off. Where are we going with this? 151616151550F00, and then yeah, I must have taken my foot off the brake completely there. So the other interesting thing which we can look at here is what's the time between each of these frames as displayed. So let's add that as a column. I need to pull that over here. I don't really need this CAN protocol one for the moment. Okay, so you can see it's updating this, so it's sending out one of these messages every 200 milliseconds, or every 0.2 of a second, if you like. Nominal, there's a bit of variation there, but nominally it's about every 200 milliseconds. And you're getting an update on the status of the brake pedal. I think I pressed it again later, so we'll have a look. Yeah, okay, so there you go. I think I tried various things and pressed it harder and harder as I went. So you can imagine that's the ABS unit. If we go back to our diagram, that's this unit here throwing out this message about how hard the brake is being pressed. Now, if I have my AIM data logger connected onto here, of course I can pick up those messages and I can interpret them and then display the metric in, record the metric in my data logger. So that's how these things work. Now, a few things I wanted to point out to you, particularly those of you who are the computer science majors. The first thing is, if you're used to looking at Ethernet frames have a source and destination MAC address. Do we want to look at one of those? Yeah, go on, why not? Let's close this briefly. Open up this, because I've messed with the format, but we'll ignore that. We can look at this area here. So here's the Ethernet frame format. Destination MAC address, 6-byte address, source MAC address, and a type field. In CAN, you don't have a source and destination MAC address. So you don't know where it's come from, which is quite frustrating actually. And if you look at Loopy Bunny, he's actually determined where some of them come from. But you can't really determine it from the actual message. There's no way of figuring out where it's come from because it doesn't have a source MAC address. You don't really know where it's going to because it's broadcast. It's not what you would call unicast in Ethernet. So basically, anybody who's interested can listen for these messages. They all come out onto the bus, and you either listen to them and decide you want to process this particular message ID 168 or hex 888, or you decide you don't want to, and it's as simple as that. So that's a bit of a difference, and then the other thing is the messages are really short. So whereas you would have a payload in Ethernet of say 1500 bytes, you've got 8 bytes here. So one final thing I was going to show you was I have started to try and write a decode for these. So let me see if I can enable that. If there's anybody watching this who knows about writing Wireshark decodes, you're probably wincing at this point because I've written it as a poster sector. But let's not get too hung up on that. So you can see here, for example, I've managed to figure out brake force. Torque setting. I don't understand this. I don't think I had the car running. Maybe I did have the car running actually. No, because the RPM value is 0. So you can see my decode needs a lot of work. There are some messages which aren't in the Loopy Bunny table, so I don't know what they are. Some of the CAN IDs, let's add the CAN ID in here. There's a column. So you can see we've got some CAN IDs 416 or 1A0, hex 200, 2dog5. We don't know what they are. So I've got to try and figure out what they are. And I haven't done the extended sort of decode other than the fact that I've taken the Loopy Bunny explanation for this CAN ID and added it in. And then very occasionally, like these ones here, I've attempted to do a further decode. But these are obviously not working correctly. So I need to do some work on those. When I do get further with this, if I complete the decode, I will make it available. I'll figure out a way of sharing it, and as I think I mentioned in my last video, I do have a GitHub repository. I could probably share it through that. But anyway, one way or another, I'll share it and I'll explain how you install it. It's really easy to install. You just copy the file into a certain location, and that's all you have to do. I don't think I've got much more to tell you. There's not much more I can tell you at this stage. I'll try and add some things, but if we were just to summarize, in summary, you just got to remember that what this protocol is trying to do, it's just trying to share information between a number of control units, and it does it in a broadcast manner. So it just flings a message onto the bus, and if you're interested in the message because you're interested in this CAN ID, then you process the message. If you're not interested in that CAN ID, you just ignore it. And that's how this thing works. And probably the only other thing to remind you is that, or a couple of things, not everything that appears on these CAN buses will appear on the other CAN buses, because I think the JBE does some filtering. Well, I know it does, because it does for the K line. And the other thing is that when you are using a scanner and on an E87 N45 car, and you try and pull information out of the modules, that information is not going via the CANBus. It's going via this thing called K-line, which is a low speed additional connection into each of these units. So I hope you found that useful, and I'll keep you informed as I make progress.